mentioned this already. I'm a little froggy. I'm still trying to speak up, so I'll do my best today. One of the things that I think is at least a direction that we can utilize in terms of seeking something. So there's something that we would like to have out of AI that we really haven't talked about too much in here. But I think it's a good time to have that discussion. There are, in fact, as we said, as you guys know, two sort of definite schools with regard to AI, strong and weak AI, right? We live in the era of weak AI. We don't live in the era of strong AI yet. I don't care how many people are telling you that it is, all right? And if it's been built behind closed doors somewhere, quite frankly, I don't think they'd be able to keep it under wraps, all right? That'd be a heck of a thing to pull off, all right? So maybe, who knows? It's possible, but I will say right now, no commercial product, including even the most advanced GPTs, are capable of what would be considered strong AI behavior. Why? They cannot tell you how they came to the conclusions that they reached in the process. There is no explainability in the background of the system. Now, functionally, there's a couple of problems with the idea of explainability, and it relates to the concept of research within artificial intelligence, especially as it relates to deep learning. So you guys can track with me real quick as I'm going to talk about this, is if you noticed when you were training your networks, they don't perform consistently because of the fact that they're randomly reinitialized whenever the network starts again, right? So think about the number of parameters that are in place in very large networks, especially large deep networks, and think about the idea that all of those systems are randomly initialized each time the network is started training. Now, we have methodologies to try to attempt to stop the system from getting caught in local minima, right? We have simulated annealing where we change learning rates. We haven't talked about it a ton, but you guys have played around with it to see how that works. There's a couple of additional methods that help us overcome some of those problems, all right? That's the split between what I consider conceptual and practical, is the methodologies that have been implemented are the practical ones. The theoretical problem still exists, that there is a likelihood that if you're taking a relatively greedy approach to a problem and you're just generating the best possible outcome relative to the instantaneous gradient assumption, you're going to make some bad assumptions. From that perspective, we say that not every model is going to be able to be perfectly converging to ideal solutions. No matter how it is put together, there is probably actually a variety of ways in which a randomly initialized system could come to a convergence of reasonable performance or even good performance that is completely separate from and not identical to another system that performs very similarly to it, right? So performance characteristics don't necessarily dictate the underlying processes. With that said, there is recent evidence to indicate that vision models tend to think alike, all right? This is super recent, as in I read it like day before yesterday, okay? I'm talking to you guys about this because it relates very specifically to what we're going to talk about today, and that is the idea of the model attempting to, what the term would be, elucidate for you, right? It's attempting to make lucid or to make rational or reasonable the underlying processes that it has taken in order to get to its conclusion. So not only do you know now what the system has classified the object as, but you now have an understanding of the localization of where that object is within the vision framework. Now I'm not certain which came first, chicken or the egg with regard to this, because I think in a sense this grew out of a necessity to try to understand what we might be able to change in order to be able to make the model better, right? How do I parameterize it in such that it gets better at finding the things? And let's go out and look at it and say that which is measured is that which is improved. So if we make a model and we say how well does the model do at localizing the regions of interest with regard to the pixel on pixel level of where the information is coming from, we looked toward the end of the last time at a visualization of how the model is finding localized detail. What I'm indicating here is if the goal is to get better segmentation, right, that also has the desired side effect, or potentially has a desired side effect, of reducing error with respect to what a human might consider to be the localized region. Now, how did the models learn where this stuff was? How did they get the capacity to localize the elements in place? A lot of times this data is labeled. It has already had extensive human derivative labeling. There are also some unsupervised methodologies, right, effectively kind of a clustering approach, that look at the information density characteristics of subspaces, right? So as kernels successively activate for the detection of dog, the detection of horse, detection of person, we have sequential layers that activate only on sub-features of the element, the component of the system that is put in place. There are some interesting elements to this, right? Bounding box characteristics. It actually used to be relatively difficult for bounding boxes to overlap like this, right? So in some of the early systems, they really struggled with being able to localize that two things could effectively be in the same space. When we started working with more successively deep convolutional systems, we started with more and more abstraction, such that there could be a difference between the person and the animal, right? So we say, I can actually have kernels that activate and create a variety of different perspectives that effectively extract the human and the human's features from the equine features of the animal where they overlap each other, all right? So we have an intersection between those two objects spatially that we must attempt to deal with structurally and semantically, all right? So oftentimes we talk about this idea of segmentation, of being both semantic segmentation, that is to explain to us how the elements of the image work together in order to make up the scene, as well as to just do localization based upon the regions of interest or pixel level structural elements at play. All right. One of the interesting things was a tool was put in place at some point in time in the development of this process, and it's a little vague. All right. The reason why I can't point to, it happened on August 13th of 2014 or whatever, is because a lot of this stuff happens behind the scenes, right? We only really have the launches of these models when these models went more public and more open. So we could say that there are sort of epoch dates as these networks became published and started becoming open sourced. And a lot of the early processes were actually open source, right? There was a lot of academic pressure to it. So let me explain to you the reason why I say that academic pressure characteristics with regard to something like image processing and segmentation still have a lot of pressure against them with regard to that scientific publication paradigm. How repeatable is the process of training a network? Limitedly, right? At least with the scope of how we're going about it. So I could potentially farm out the elements that are structured into the network, the items that are put into the randomly structured arrays from a seed, right? I could use a seeding methodology to do that. It's really hard when it gets into a big network, right? Because which segment of the seeded pool, right, gets what? I have to dictate some sort of cyclic algorithmic process for where I initialize pieces within that space. If I put the items in the wrong way, we notice two things happen. One, computers are relatively good at generating random numbers for a while. What happens after that? You start to get sequence repetition, right? They did a good job at creating some sort of cyclic process involved in it, but then if you get a long enough string in them, you can start to notice cycles and patterns in the distribution. So unless we pick a random order in which to populate the elements of the system, you'll start to notice that layer by layer the system starts to take on a resonance characteristic, right? It starts to resonate in the same way that the kernel function activations resonated. You guys remember the little swirl shapes and how those swirl shapes were repeated throughout the space? Resonance is a natural consequence of repeated number systems because they're usually done by procedural construction via long chain algorithmic processes, right? So the only way we really know how to do this is sort of a roulette, round robin, spatial random selection process. So we start off with random Gaussian seeds, and we start by sort of sprinkling things around as quasi-randomly as we can. So unless I start off and I tell you, here is exactly the matrix of my initial training process, then you don't even know what I started with. Let me go ahead and throw in another random process. The selection of which elements were in the test set and which elements were in the training set. The sub-selection of the K folds that were utilized in each of the localized training assessments, all right? And then even further from there, the batches that made up those folds. So now we have random selection on top of random selection on top of random selection. Sometimes I would say that the current buzz around getting published in machine learning space is backing up a truckload of dice and getting a Yahtzee, okay? It doesn't feel like there's anything that is procedurally driven in terms of being able to explain to you how to repeat my work. So if you can't repeat my work, what's the problem? That means you can't invalidate it. Science relies on the construct of invalidation, all right? I don't like the term settled science. I've never seen that as being useful because that's not how we learn, that's not how we think, all right? We can't have things that we constructively feel like are laws, but guess what? On a regular basis, you read things in articles where people go, oh, somebody's trying to disprove some such Newton's law, whatever else. It's like, yeah, we can find exceptions to rules outside of it. Machine learning systems are the same way, right? They are stochastic, they have random characteristics to them. The procedural training process makes it incredibly difficult to get a singular handle on a optimal workflow or even to be able to translate that workflow to someone else. So if I select a slightly different order of components that go in for the batch training process, I could effectively have an entirely different network. Given that, as I said previously, on a long enough training timeline, a lot of the tools that we're going to talk about from a hyperparameter analytics perspective and from training and gradient optimization standpoints, which infers for both the fully connected and the convolutional propagation process, are developed to try to keep the model learning and keep the model moving, such that if you leave it trained long enough and you can avoid it overfitting, then you should theoretically be able to allow it to continue training for an indefinite period of time, and eventually what should happen at that point in time. If the surface of error in that particular subspace is effectively known, and we have information that is sufficient to recognize and give us a visual approximation of what's going on here, we should be able to confirm that the output of this system registers to what we as humans would think, right? It should converge. Effectively, every single pixel in this image that a human would label as being part of the dog should be found by the automated process. Let me throw another monkey wrench in the works here. What happens if the human mislabels the image target? You guys that were in my statistical learning, you remember that I characterized noise as process variance? I would say that it is a biologically inserted noise. It is bad human behavior that corrupts data sets. That I can actually give you a picture where exactly the right pixels are selected of the dog, and then I can give you 500 other pictures where several of the pixels are misattributed. The system actually has to be able to try its best to learn from what it was given, but also attempt to do something that seems really crazy and pushing into the AGI, strong AI space. All right, what is that? We try to say that it needs to be able to exceed the quality and performance of the individuals that were actually labeling and tagging the data. So many times the reason why we can only get 98% performance, 97, 93% performance on some data set has very little to do with the model's capacity to capture the variance, because there's a lot of capacity, a lot of variance capture and explanation taking place, But if we see something that's a misalignment between what our expectations are for the ground operations and the actual output of the system, we have to understand that it's probably just working within the limitations of what it has seen along the road, okay? I want to load something up real quick, because I'm going to need to look at it in a minute, and it takes a little while to run, so. I don't know as I have to run this, but it's going to make me sign in. We'll let that simmer in the background. I'm going to have to tap over to it a couple more times. I wish I could split the screens here, but the ILE doesn't really let me do that. So this is a fairly obvious image, right? Structurally, we can see a lot of things that are doing. Anybody worked with a computer vision toolbox that facilitates this, outputs this? Okay. I've worked with them a few times. Yeah, you have, Sharon. I would imagine you have. There are segments of a couple of programs I've worked with in the past that use OpenCV. Have you guys know what OpenCV is? All right, Open Computer Vision Database. OpenCV does have a object recognition pipeline built in, right? And this effectively is the object recognition pipeline that's built into OpenCV. So if you can actually download that and install that, or even run it in a Colab instance real quick, find out that it's capable of detecting a lot of objects. Why is it a truck? And why is it a car and it's calling a truck a car? All right, that sounded a lot better in my brain. Why is it is a truck and it is calling it a car? Why is it doing that?
There's a couple of reasons, I think.
Sure.
Either there's no truck category, or I think from this angle it's very hard to tell that it is a truck.
Mm-hmm.
It looks like, yeah.
What is it that we're doing that tells us, what's the quick inference that we're doing that tells us it's a truck? Why might we presuppose it's a truck? That's true. It's on a farm, right?
Yeah.
You don't think about a car being out at a place where you got animals, right? There's farmers drive trucks, right? So I'm just saying a quick inference that we might do if there was a truck category. Actually, this matters. This matters more than you might think. It's not really as much of a joke as you might think it is. Because the probability of assignment of the likelihood of a vehicle being detected in a specific space will be involved with, right, the likelihood of that type of vehicle being found in that space. So if I classify the rest of the visual information in the system as being farm-like or rural environments where trucks are more frequent, then the softmax of those feature components that make up the car image, right, would end up maybe pushing into the truck space because of the fact that they could be recombined, right? So we say maybe we'll take a different look at it, maybe we'll reconstruct it semantically, but we do use context, even as humans, to be able to determine the likelihood of a component, especially if this piece was a lot smaller, right, and we could only see maybe headlights or tires, right, or if it was really sort of vague and cloudy, we could probably still guess that it was a truck because of the things that were around it. All right, human, person being on top of horse, also, right? Human underneath horse, probably not as much.
God.
Right? That's not a good, that's a scary image, right? So we don't want the horse trampling the person. But it makes sense for the person to be up on top of the horse, right? What other things do we have? We have another person in the background. A person's really small. So how can I tell it's a person? This is an interesting component and something that I mentioned to a couple people that were up front toward the end of the last lecture is one of the really cool features of successive filtering and pooling is that if the image component is really big to begin with, what happens as you take filters down it, right? You take filters, it reduces in size. So it reduces in size and then only the pooling components are kept. What happens if the component is really small to begin with? As that feature is detected and then pooled again, what happens? The feature actually increases in size relative to the activation because the components are kept. So relative to scale, as long as the features are present at an appropriate scale and can be detected with deciding power resolution, then the system should be able to treat two differently scaled models of the same object in the same space and recognize them both, because different features have been activated in each of these representations. What's the other thing when we were talking about when we were looking at LeCun's slides, right? If you change angle, right, which way you're looking at a person, the guy in the top right hand is walking away, right? And the guy on the horse is looking towards us. They're both considered person because of the fact that person has been trained with a robust understanding that people can be facing in all different directions, right? There are a set of features that are not present on person in the top that are present in person in front. There's also a set of person in the front that does not have, his back is not seen here, right? So there's feature components of his person components that the system is looking at, largely the intersection with the features that are present and the likelihood of those features being present in that configuration in order to give you a sort of post hoc likelihood of that particular image, person, that space containing those elements. The segments provided here are effectively just an annotation characteristic with regard to the original spatial activations of the kernels localized and up projected through the kernel pooling operation, right? So we are going to have a region of abstraction operation from which we're going to do an initial input image, and then we're going to extract several different potential proposals for operation, right? So this is a recursive operation with regard to what's called an RCNN operation, right? Recurrent CNN operations allow us to be able to utilize potentially many even overlapping windows of image inference and interest in order to be able to localize the compute components. A warped region is constructed, right, out of the operational components that make up the image space in order to stretch the feature fit based upon scale and view components. All right, so the warped region is then reprojected into the CNN compute feature operation, and we're actually going to utilize multiple different perspectives from the same image frame, extracted from the original image frame at the resolution that is appropriate for this particular CNN. This is an interesting component. The input scale of a CNN is fixed. They're a fixed structure, right? I can't put in differently sized images through the CNN. Some you can. There's some exceptions to that. Newer systems are capable of doing that. UNets are capable of inserting images at different levels. We'll talk about UNets in a bit. But for traditional forward CNN architectures and RCNN architectures, we're going to treat those architecture components as fixed arrays. Part of this is because of an array scaling characteristic to the back ends that requires the allocation of the memory space prior to the task execution, all right? Another portion of it is that the features found within the image space have to have some degree of spatial compatibility with one another, right? We shouldn't see radically different spatial differentiation or rescaling necessary in order to get the images to the same size. So what we start off with an ROI, and then we span or stretch the ROI to fit the input space of the CNN, right? So even though that original space was sort of a rectangle, right, we're going to wrap it to that square that's the appropriate input space. Interestingly enough, that warping operation doesn't affect the CNN's performance much. What might be a reason behind that? It's already going to go through a significant amount of transformation based upon activation and pooling. Right, so the activation and pooling operations are already going to transform it pretty heavy, so a little bit of stretching doesn't really affect it that much. Also, we occasionally sometimes will introduce something that I haven't talked to you guys about a lot, that you've played around with as a parameter, and that is we can add things like noise, or we can change or modify the input space to enhance the informational characteristics that are present. Yes, Shane?
So the wrap region, like you're wrapping in the region, does it
No, it's not a wrap. It's not wrapper. It's warping.
warping? Sorry,
Yes, I'm rescaling the image. I'm
warping.
rescaling,
Does it
yes.
doesn't it add more noises to that?
No, because it's just a transformation, right?
Okay.
You could say that that distortion
Yes.
is maybe a type of noise by a non-uniform stretch operation, but it might actually enhance already latent noise. That's a possibility. But since the operation is relatively symmetric and fixed, it should just be rescaling any of the components that are already in place. So if we think about it from an information standpoint, we'll have hard eigen components that will be spatially transformed appropriate to the diagonal matrix. But we'll also have components that will have asymmetric stretch, meaning that they will not have quite the same as their original shapes. We do something called augmentation, all right? So, we'll walk through that tile in a minute, but and I need to tap back over to that and see whether or not I'm ready to go with the next tile. Yep. Okay, ready to go? Just doing the dishes here. Okay. I want to show you guys an actual runtime for an image segmentation operation using Colab. Okay, I don't know if any of you played with it, but it's just an operation to show you some stuff of what's going on in the space. So the compute operation CNN features for the warp input image space experience a little bit of modification, right, such that they're rescaled based upon the original inference. And a lot of this original inference are the proposed extraction regions that are put forward or done so by utilizing some fast transforms and fast spatial localizations where the components of the image space that contain the highest frequency elements are selected, right? We say we select candidates for regions of interest that look most like something we get something out of. And that process of candidate selection can actually be also enhanced by getting some feedback from the final capacity of the model to detect and segment the objects of interest, right? This whole thing can have a circular relationship where the quality of the output can come back in and help inform better which regions to be extracted in the future, right? So that's where the recurrent component comes in, is that we get better at guessing which regions are most involved, and the features also adapt to being able to recognize things like warped components, which is interesting because you would think that, okay, being able to recognize warped images doesn't seem like it would be a high priority for the system, but it does anyway want to try to make maybe more than one filter that can react to the same target at different scales. But once it's gone through a couple of sequences of pooling, a lot of those spatial warping characteristics of the activation are effectively gone. They've been rescaled, compacted into a lower scale representation space, and we call that sort of a latent feature space. Now, why would I install noise in this system? Why do I put noise in? That seems terrible. Why would I add noise to the process?
More robust model.
Okay, that's good. That's a good inference. Okay, why? How does it make it more robust?
If your input data is more noisy than your training data or whatever, you'll get better results.
And that's pretty much exactly true. All right, that would be probably a textbook definition of exactly what the concept of noising would input. As long as the noise has relatively symmetric characteristics that would be normally occurring noise characteristics, right? If it is zero mean Gaussian noise, randomly distributed over the surface, then that noising characteristic should effectively start to model the idea of there being real noise in the original data. If the original data has some noise, and then you imagine effectively a worst case scenario, right? Let's think about it from the perspective of your ability to recognize audio. Degradation in audio quality is really kind of those funny things. It's like you can have a conversation with really, really bad audio, right? You can still talk even though it's got a lot of noise in it, right? A lot of crackling and speckling and a lot of degradation. The concept is that effectively there will be a point at which you'll not be able to understand it at all. okay? It will eventually, the noise will overwhelm the signal. But if we imagine that we have a relatively good call, right? It's got some noise in it. We take that call and we add additional noise to it. We train the system to recognize the audio from the bad noise signal. Then when it's actually applied to the good quality phone call that you're listening to, you go, wow, this is so much easier than it was beforehand, right? You're training it to listen harder. So the listening harder process also encourages the model to do a couple of other things, because the noise will mask and distort and add and take away from some of the features within the system as well. So it has a bit of that masking characteristic by which some of the activation components of the original image will be covered up or not fully available to be detected by the model. As a result, by not seeing everything, it is a similar process to kind of a k-fold process or a batching process, where you're limiting the amount of information the model can train from at any given moment within that particular system. Okay, so we have an output classification layer once all model components have been characterized. Classification layer is added in. This is a softmax once again, right? RCNNs generates these bounding box ROCI components, right, where we have CovNets working on each of the relevant bounding box spaces of the image. This is how we were able to accomplish the fast image localization and segmentation processes that are used for things like Google image search, right? And the semantic annotation that goes into something like Facebook when Facebook tags you in a picture. So Facebook creates the candidate log list of regional components using a fast face detection mechanism like dlib or a fast har cascade, right? It finds two eyes, a mouth, and an oval. Okay, it says here's the candidate ROI, and it passes off the small region of interest off to its own parallelized ConvNet model, which will tell whether or not the person within that database, right? It'll construct the feature extraction out of that process and then attempt to match it with the localized graph of connectivity. We haven't talked a lot about graphs, but I'm going to try to see if I can tack a graph discussion on the end of the semester, right? There's a lot of stuff to do in this class. I feel like it's kind of an inordinate amount, right? There's just so much happening at once. It's crazy. I can't get out in front of all of it. But graphs are a type of network, right? Kind of like a neural network, a Boltzmann style machine, where connectivity between the nodes is the connectivity between you and another person, right? There are people within that node connection list. And so Facebook, once it detects the face, throws it through the ConvNet, gets the feature components for it, it will softmax those features against like 3 tiers down your connection list, right? So it goes to your immediate adjacencies, their immediate adjacencies, and their adjacencies, pulls back the feature list, and attempts to see whether or not any of the features that it extracted from your face line up with the features from the faces in that list of individuals. It can continue expanding that search out if it doesn't find a solution, right? But if you're taking a selfie and you post it on Facebook with somebody you know, I don't know if you guys have noticed this, but it will show an ROI around outside of it and suggest a tag. Matter of fact, it does it autonomously now to the point to where tags you have to turn off the ability for the system to take your feature tags out, right? Relatively invasive in certain perspective, maybe considered a feature for some people, for me a bug. But I look at it and say this idea of composing multiple different parallelizable models is relatively interesting because the fact that it really solved a problem that I think many of you would realize from not just kind of a cursory indication here, that for large images with relatively high resolution, attempting to either crunch them down into small enough spaces for the whole image to be run through a standard ConvNet, or trying to run them through at their native resolution, both are going to have problems with regard to the memory space necessary to accomplish that. So this idea of breaking it up based upon regions of interest pre-selected by external methodologies cleaned up and optimized the method for passing off information throughout the layers and added a degree of parallelization along the way. All right? So fast RCNN methods do this ROI detection and map framework process, and they do a joint extractor classifier regressor framework, right, such that this whole system together optimizes not only the selection of the ROIs, but the parallelization of multiple different models to recognize components of the ROI, and then a balance operation for the classifier to be able to fit different operational classifiers to the paradigm. That idea of actually setting up a network to do a similarity analytic, right? That isn't exactly a neural network style problem. We just take the feature layer that would have been the flattened feature layer out of the last portion of the CNN and do a cosine similarity analysis to the previously extracted features, right? So it's just going to be a array cross validation operation. It doesn't utilize something like a trained, fully connected network at the end layer, because the only reason why we need that is if we have trained that individual system to recognize those individual people. There are two ways to go about this. You could actually create a system. Let's say you're trying to build, once again, I give my biometrics example because I've spent a lot of time in this space. Say you're trying to build a biometric system that does access control for a physical facility. Let's say you have a series of cameras, and those cameras are able to watch the space and see people coming through. You could have a classifier built specifically that's trained to recognize and classify, categorize each face that's found in the system based upon whether or not it's a face that's acceptable within the list, right? Treating each one as a category. So if you treated each person that was allowed to be in the space as a classification output category in that last element of the layer, right? It'd be the same as trying to classify the digits like we were looking at in MNIST. So each person would get an authorization list. You'd say the likelihood that this person belongs in the space, and if they didn't belong in the space, what could happen? You could elevate the warning, right? Attempt to get a different view on them and maybe be able to even create operational access control. That's a, how would I say that? That's a moonshot kind of project, right? So some people are working on it. There's interest in development of those kind of projects, especially from the military side. I've worked on a couple of projects like that for the Air Force, and they're interested in installing them in places like airports and other facilities, because you could put a list of individuals that were not authorized to fly within the system and then detect their presence if they ended up at an airport with the system in place. So you only need to have a limited number of classes in place in order to be able to make that work. But the same concept is at play, right? It's a similarity adjacency analysis between the extracted feature components, and it'd probably be less practical to build a network and train a network, right, to automatically do that process whenever you can just compare the features with one another once it goes through the model. Okay, so training time, operation, hours, right? We started off with standard RCNN mechanisms where the spatial flow and the extracted component characteristics were something like 84 hours of runtime operation, right? And the actual region proposal and extension runtime test time operations were somewhere in the neighborhood of 50 and 47 seconds, right? So 50 seconds for both operations, right? Both including and segmenting proposed region operations and the external region preparations included versus excluded. Okay, so this idea of saying that we saved some time on pushing down RCNN's area of effect by pre-segmenting the image, where we're already cutting out the ROIs, that seemed reasonable, right? But SITNet and FastRCNN pushed these times down from 50 seconds to fractions of a second, all right? Runtime for FastRCNN detection with spatial localization is 0.32 seconds for the same frames that were being run previously. So we started off with an architecture that did the pass-forward operation for simple compute operation pass line and converted it into a single framing process where we had both the extractors, classifiers, and local spatial regression all within one module. They were able to share information between them, and it massively enhanced the runtime components of it, all right? So the other thing is, if you have to pass it between modules, you have to copy memory. But if it's all within one operation, then you can just pass elements by reference. You don't actually have to move them in memory. That massively cuts down on time. So a big chunk of this is an optimization framework by simply thinking about how many copy ops we're going to attempt to put in place in order for some of these things to happen, right? So if you're working on the original image and you can pass the original image framework elements to multiple components simultaneously, right, then you can be doing either the copy or bifurcation or core operations all at once from the same memory space without having to pass access around at various levels of modules, okay? I'm going to hop over here and see what we got. I think the one thing I'm going to be dealing with now, it's going to be problematic, is this data set takes a minute to load up. So, but we'll see what happens if I get there. Okay.
Faster.
Yeah.
It
So
just keeps getting
faster, even better operational runtime operations started to take feature maps from the full spatially localized regions, because what happened here? Now we have access to massive amounts of memory. This is another consideration. Early on, one of the reasons why we were limited to being able to run limited to certain scopes of regional components and characteristics is because we just didn't have enough memory to both extract the full feature set from the full resolution images and handle all the different convolutional range sequence proposals. Now we're able to do all of this in GPU compute memory, all right? That was one of the big epochs that changed from the early operational systems that were designed mostly to run in CPU to fast RCNN and RSPCNN and all the other ones that are coming out now, where regions, proposals, and ROI pooling, and then operations on ROI pooling are all handled in the model as a workflow, right? They're feed-forward processes. They get handed off into different modules as they're going forward. So once we collect all the content layer feature components, we can start mapping with and messing with the feature maps and spatial proposals, right, as if they're already put in place. Interesting component of this is I can do the proposals to the ROI operation segmentations and classification of the regions. I can do those things effectively simultaneously, right? I can already be copying those ROIs over as they're detected from the candidate space. So as I said beforehand, a lot of this has to do with optimization of words stored in memory and how it's being passed off between elements in the system. So faster RCNN pushed down from something like runtime for contained scale at about 2.3 seconds for the structured full frame information. Remember we said that we're going to be comparing these now from the concept of running the full frame without the ROI. So instead of doing it for regions of interest at a time, we're now just considering the whole frame. So fast RCNN doesn't have a way to compare its performance to the performance of the pre-segmented image versions that we were dealing with in RCNN and fast RCNN. So we have to compare them to the full frame operation. Why doesn't it have the segmented version? Because the segmentation happens after the convolution, right? So we put the segmentation after the convolution, we inform the segmentation with the convolution feature data, then we've already gotten the feature extraction process and that sped it up by yet another full order of magnitude, right? So we were basically order of magnitude in SPNet, and then probably about 50% increase for fast RCNN, but then we went for a full order of magnitude again with faster RCNN. That interesting component that's at place with that faster RCNN, right, was that the features were already present, meaning that they didn't have to get pushed off in all of these parallel pipelines in order to run. So the moment we figured out which features we were working with, the rest of the process was like that, right? It's already in memory, it's already present, it doesn't have to be extracted after the decision-making process takes place, and the localization capacity of finding the valid regions within the feature space was already handled by the ConvNet, right? It had already found all the features of interest by the time it got up to the spatial level, so they were able to utilize spatial components in order to help with detection of the ROIs, right? You didn't need an external system to tell you where the face was. You could use the ConvNet, use the activations of the regions from the ConvNet to select the regions of interest based upon the activations of the kernels from the ConvNet. Effectively, the ConvNet is already handling the candidate process for the ROIs for you, right? It's saying, not only do you want this region, but I'm telling you the reason why I selected this region is because the filters that are most commonly correlated with the item I'm looking for in this space, or a item of this type, have been activated, concomitantly activated, right? So it's already doing the thing that we were interested in having it do. I'm gonna go over here and see if I've gotten there yet. Yep, okay. All right, so I'm gonna do a couple of things here. I'm normalizing the output masks, right? And then I'm loading the data point image framework. I'm now characterizing batch and train split operations and splitting up the images into test and train. Notice, once again, as I mentioned beforehand, these are random operations, so they're not going to work consistently such that this isn't really replicable. All right? Now I'm going to implement an augmentation class. This takes the data set that I already have in place and does things like flipping it around, right? Random flip on different horizontal axes in order to be able to create different versions of the image. That enhances the process as well, okay? Training structure is instantiated here in the TensorFlow format, right? TF form. We can do this a little bit faster with Keras by instantiation as well, but this shows you what it's like to be able to do the framework for that range, all right? We're gonna define the display operation here, and I'm gonna output train operation for mask to show two output options, okay? So these little pictures of little puppies, all right, which are awesome, and they're already segmented. True mask has already been put in place in the system. That's what we're gonna utilize as our training framework. Now I'm gonna define a model, okay? We're gonna see this visually, so I'm not gonna talk through it a ton here, but data is loading from the TensorFlow CAD for a 64 by 32 by 16 by 8 by 4 operation with block styling, okay? I'm gonna stack it up and put the pixels. This puts the pick sample subspace in a tensor to be able to pass it off to the system. Once again, notice TensorFlow, right? It stacks all the images in the block up. I'm going to define the output model characteristics that are going to go through the downsampling and spatial resampling process. And then I'm going to begin to classify the output space here, right? This is the definitely is object, periphery of object, and then background of object. Those are the three classes that are being detected by the system. I'm going to implement a pilot modeling. Okay, I mentioned earlier that we're going to be able to look at what the model actually looks like. This is the structure of the model. Okay, shows how everything's being passed off. You start off with the layer input spacing, right? Model characterization for input spacing shows 128 by 128 by 3 is the input size of the images. All right. Then we pass off that system through these kernel operations, right? 64 by 64. 96, 32, 32, 144, 16, 16, 192. Notice these are getting bigger and bigger as it goes through the conv, right? 8 by 8 by 576, and then 4 by 4 by 320. Notice there's some cooling operations that have to happen in between these. And I'm passing this off into multiple segments between the sequential space. There's a little bit more complexity here than we have in a standard concomitant model, because we're actually going to be passing elements of the original image framework to different ConvNet layers in order to be able to train and optimize the output localization. Okay? So I'm going to define the masking operations for the output, and I'm going to define the methodology for outputting the prediction framework based upon the operation masks. Okay, this says that what's returned from the predicted framework can now be mapped to the outputs on the image, such as the original image is added with the mask in order to pass off from the create mask operation. So create mask generates the mask, and then mask is passed over the image, all right? So we're going to indicate the show predictions operation. And it's going to run a simple time step up here. And the original input image, the true mask operation, and notice the predicted mask. Not so great, okay?
No,
Not so great,
not at all.
okay? We're going to call the callback mask operation, and then we're going to call 20 epochs of the operational history, meaning that this is going to start training the operation, and it's going to run for operational runtime of 20 epochs. So we're actually gonna be able to see it run here in quasi real time, okay, once it comes up. Each of these takes about anywhere between 30 and 40 seconds. So they're not gonna be fast, but we're gonna be able to see a couple of them as it's moving forward. Notice a couple of things here. We're able to do almost everything that we need to do for an improvement of the model, right? Now I'm actually training this model in Colab. This doesn't require anything from you guys to have anything locally installed. We can run all of this as already been developed. First epoch did okay, right? Second seems to be improving.
Third,
See what happens?
it's improving slowly.
It's slowly improving, right?
Yeah.
And it's doing so by the process of determining effectively the difference or the spatial distance between the true mask and the predicted mask in that framework. It's passing it through the kernel activations and then trying to find an ideal set of elements that correspond to the output classifications in the true mask paradigm. So it takes effectively input, output, right? Or excuse me, input, target, output, right? Error is effectively the difference, right? The absolute difference between the input and the target. So any component that's mislabeled at that point in time, mislabeled from a localized perspective would be considered what? An error of a specific subtype. Notice it's starting to clean up some of that noisy edge characteristics as you're training further into the system. And that idea of cleaning up some of the noise along the edges is intended to try to make the system be a little bit more tight. It's the loss function being utilized here is incentivizing it to try to minimize the space allocated to the periphery. So there's actually several different loss functions running in the background on this on TensorFlow because it's trying to figure out what the percentage of or the likelihood of any pixel within the image to be of a specific class as well, right? So it uses a prior and density estimate function for the original spatial localization. Not terrible, right? Predicted mask operation actually seems like it's doing okay. We're somewhere in the neighborhood of about 14 of 20 epochs now, okay? So we'll be able to actually go and look at this once it's done, and we'll be able to do a performance evaluation on the remaining part of the system. So we're at 15 epochs. Notice some of the things that are interesting is that from epoch to epoch, it tends to have a little bit of flexibility with what it considers to be in versus out of the components at play.
Yep.
It's maximizing based upon local kernels that are the final activation step of the process, plus also doing what? Propping some of the error back to the previous layers. Those layers are still being optimized based upon local greedy activation to try to find an optimization between finding features that correspond to this spatial localization, right, the frequency of the items at play, as well as trying to provide an improvement in successive performance, such that if the feature is detected and then successfully localized, it will continue to be present as the model goes forward, because the pooling operations, if it is a highly active feature, then it will be more likely to be picked up by a pooling operation, right? So the most successful features from the pooling operation are the ones that are going to kind of be considered to be the most viable along the way. I think the predicted mask in the end is close. This one's interesting because I'm going to point out a massive error. It's placed elements on the target side outside the element layer mask, right? Over here in this corner.
Yeah.
Big no-no, right? Say no. Object not leaking out of container, all right? So that's the problem right here. We have it, it's leaking out of, it's not a closed space, it's leaking out like,
Little leak, yeah.
yeah, it's a little bad, okay?
But it's not
So
too
let's look at the loss history. We're gonna run this as an output.
bad.
And we notice a couple of things that happened here.
Start to become.
It started to maybe experience a little bit of overfitting.
Yeah.
Probably really early on in the process it experienced some overfitting, way faster than we thought it was going to. We said, hey, it's doing good, and then all of a sudden
It just.
it started memorizing, okay? Now, does that loss divergence cause like significant concern for me? Not so much. I'm not really that worried about it because val loss can be problematic at the scales that we're working at here. There's only a few thousand images in this, all right? So we're gonna go ahead and show a predicted batch for the output, and we'll go ahead and show you a couple different targets, all right? Here are three masks, 3 candidate masks. We say this kind of gives us the opportunity to do what? Visually validate the operation of the system here, right? That one's not bad. That one's got a little bit of bleed and a little bit of localization cooling issues at the bottom. We can see maybe why, right? Because getting the foot in there. Now, is the mask actually corresponding with the spatial characteristics of the system? No. The masking is actually in error, okay? So that's one of the things that I wanted to show you along with this is I want to talk to you about the idea that even the data that you get within the system can be problematic, all right? So we're going to try a few different batch operations here for a imbalanced class output operation. I don't know if these are going to run or not, but this is going to attempt to update some localized accuracy fit. I'm going to have to go a little bit early today, because I've got a test in my other class that starts right after this one. But we noticed some things that are happening here. Load this up just a little bit better so we can see what we're looking at. I know in-class demos are not the most engaging thing ever, but I wanted to try to show you what's happening, what we're looking at, kind of give you some information about what you're seeing. The number of epochs, right, that's being put in here, this value of 20 is just arbitrary, entirely arbitrary. The same way that you guys selected the number of epochs for your system was arbitrary, all right? One of the things that I will say about that is giving it to you as sort of a, here's a thing, change it, without necessarily thinking about a lot first of what it means and how it affects the system is intentional. I wasn't really trying to over-direct you as to what was happening. I was trying to let you kind of discover it on your own to a certain degree. You can correlate what it means to let it train for longer, right? We tend to think more epochs means better accuracy, right? That's always the answer. No, we notice whenever we're looking at the output operation, we see that we have that diminishing return or the characteristic divergence between the bias variance dilemma happening very early on in the system training. So what we might actually have to do is we might have to call some other operations, right? We might have to change the batch sizing. Changing the batch sizing to a slightly smaller batch size and increasing the number of epochs might allow the system to continue learning longer, right? Where it's making more frequent changes based upon fewer examples, which stops it from memorizing too many of the samples at once or trying to over cater to too many samples. But have too few samples at any given time, and what happens? The model jumps around between different localization, different local errors. So what can you do to fix that? Reduce the learning rate. So the learning rate integrates less of the relevant information per epoch. So if we make the batch size smaller, we make the learning rate smaller, we make the epochs higher, we might be able to get a model that takes longer to train, but ultimately has more robust performance. So those trade-offs where I'm talking to you about those things in a generalized sense are more me kind of going up here metagaming the system and saying there's a lot to play with. We can also play with the learning rate over time. We might want to, for a naive model, start off with a very high learning rate, right? Take big steps to start with, and then slow down. We also might want to make the determination of the confidence of the gradient based upon the relative instantaneous slope, right? Talk about Newton's methodology in my videos I'm putting together. And as I said, once we've, unexpected assertion error. Come on, Collab, you're not supposed to make mistakes. Okay. This one is going to try to attempt to do fit operation for single output sample and see what the localized accuracy is. Oh, it's not showing me callback history.
Oh, oops.
Yeah, something happened. Okay, there is a possibility something happened here at the end of this last epoch, or as it was being passed off. Let's see here. Yeah, there's a, yeah, it did run an operational, characterization, so it did an imbalance class localization. So it wasn't able to converge to ideal metrics in this case, yes.
Were the true masks here, were those unit labeled masks then, or how were those generated again?
Those were generated by somebody who was like a mechanical Turk method. I've talked to you about that beforehand, where they basically set people in front of the screen and you say, draw points to make the bounding box around the outside of it. There are a couple of different companies that specialize in it. And the weird thing is, you're actually, all of you, as I said previously, you've all been involved in that process. CAPTCHAs are actually a mechanism for attempting to sublocalize regions for image space. So the necessity for localized masking versus the ROI pre-selection, if you think about that idea that you click on the squares that contain the items of interest, you're pre-selecting the regions of interest for the model so that it can skip that whole process of the candidate ROI regions. It can just pass those regions off, knowingly containing the objects of interest. So the masks put in place here were, as I say, they were human constructed, and that means they're more likely to experience problems. What people are starting to do is they're starting to take the trained models, using them to model using them to label new data, and then using that labeled new data, right? I use this model to segment a new image. I take that mask, and then I try to train another model using the mask that I got from that system. We'll talk about that. That is a whole can of worms, okay? Because there's a lot of stuff that's involved there. So we have to be careful about what we do and what we give the system to train with in some of these cases. Okay, well, I'll see if I can find even another one of these along the way. I found one that's maybe, might take a little longer. I might have to come in and start it next time, or bring my laptop while it's already started. But you can find this. I can put up a link for it if you'd like to see it, to be able to run it in your own time and see if maybe you can make some changes to it, because you actually have the option to be able to change some of the metrics in the construction, and you can even change the model characteristics, right? You can actually go through here and change the model and try to train a different model and see whether or not it works better, right? So, okay, thank you guys. I'll see you next week, okay? Everybody saw I gave an extension for the homework, right?
Yeah.
Okay, do your best on it. Keep trying hard on that, and we'll continue to talk about it after.